Good afternoon. Glad you're still all with us. Everybody awake and having a lovely time in Australia this week? Yeah, that's why we're here, huh? Okay, I want to talk to you about some stuff that I started kind of a follow-on from my presentation last year. I'd hoped, of course, to get a lot further on the direct path that I had planned out for the year. You'll see exactly what happened. Adventures with DRI3 DRI3 is a broad topic that I created the name and then was told that I couldn't use the name for the extension, but I continued to use the name for the overall effort. And we'll see what happened. From last year, remember everybody, the balloons and the lovely party we had on the hill? That was an awesome time. I was talking last year, in fact, I showed a bunch of performance numbers about how I was going to be able to do efficient composited GL applications in Windows with 0 copies, and it was an awesome little demo. I have a KernelAPI that does all the page swapping. It really was tremendously impressive in the demo. Getting from the demo to the whole system took a little longer than I had hoped. Here was the plan for 2013. I was going to have these perfectly executed little extensions all in a string, about 1 per month. And they were all going to work beautifully together. And when you put them together, they were going to look like, you know, a necklace of gorgeous jewels. Yeah, I was going to write a DRI3 extension. I was going to write a new extension called Present. It was originally called Swap. I was going to just, go and hack Mesa to support drawable offsets again, which we're used to. I was going to do the implement this page level swapping I talked about last year, and I was going to make it all work in Gnome Shell. It was going to be awesome. Yeah, what really happened in 2013? Yeah. You start doing a little extension and you start tugging on the string of the implementation of that extension, and pretty soon, yeah, this is what you end up with in your office. I'm not going to actually read all these. I just wanted to go and through it. I'm going to cover some of this stuff. I got into a little ways into one extension. I got one diversion. I got a little ways into the next extension. I got another diversion. I had some adventures there. I had more adventures here. And then in about March or April, Eric came up to me one day and said, you know what we promised to do back in November or October of 2012? We promised to fix DRI2. That was what we promised and said we were going to do. How about if you do that part first? DRI2 is broken today. We know what we need to do to fix it. How about you get that piece working and then go have fun? Eric was basically saying to me, first eat your vegetables, then you get cake. Okay, so where is DRI3000 today? Did we actually have any success? Have we gotten some stuff done? Did I fix DRI2? Well, mostly. DRI3 and the Present extensions, version 1.0, shipped in the server. There are some advantages to being the X-server maintainer. Some of the code that I wanted to merge, it was like, I'm not going to ship your code until you review my patches. Oh, but I have to have it. I promised my employer. Well, you know what to do. So all of my code got neatly reviewed and merged in time for the merge window to close. DRI3000 successfully replaces DRI2 and fixes known issues and provides a lot of opportunity to implement some cool new GL extensions that we couldn't do in the existing system. So yes, overall, total unmitigated success. We had a lot of projects involved in this, and I think this is a lot of what was blocking progress in this area. It's just the fact that we had this many projects that I had to go in and hack on in order to get the stuff to work. And there aren't very many people who are, crazy enough to be willing to go in and hack simultaneously on this many projects. One of the side effects on having this many dependencies in all of this work was that I had almost nobody testing it at all. In fact, it wasn't until November that Eric managed to get it working for about an hour on his laptop. And as a result, it didn't ship in the current stable version of Mesa. It's just in Mesa Master, and it'll ship in the next version of Mesa. There are some things that still need fixing, but lots of projects were affected. And along the way, I kind of got diverted. There were some other fun projects that I had to solve first. That's my cat. He's another diversionary tactic that I have. When the laptop starts doing a lot of benchmarking in the middle of winter time, the cat thinks the laptop is his personal space heater. And so I want to talk about these 4 topics, which are a bunch of the work that I did over the last week, something like that. Seems like. What? Harsh, yo. Some of these did take a little longer. I want to talk about shared memory fences and why Linux's glibc is broken. Linux is fine. glibc is broken. How to do file descriptor passing and what that involved. Some of the adventures in supporting a new fun GL extension for swapping with tearing instead of swapping without tearing. And then what I had to do to convince the XCB guys that I really couldn't tolerate their event model and really needed something else. So the first thing I want to talk about is fencing. My fence that I implemented does not have lovely flowers, but at least it does have some nice serialization guarantees. In the Xsync extension, NVIDIA a couple of years ago put together this change in the Xsync extension called addition called a sync fence. A sync fence is you can have 2 X clients. One X client creates a sync fence and blocks on it, and another X client can trigger that sync fence, and then the first X client will continue rendering. Seems like a kind of a simple synchronization primitive, but what the NVIDIA stuff was really for is to be able to expose those same sync fences that are visible in X also through GL. So you can have a fence in GL and you can block and serialize the execution of your GL rendering requests with your X rendering requests. In particular, you could have an X application drawing off screen and a GL compositing manager, which would make sure that it waited for the X output to appear in the pixmap before it drew the stuff on the screen. That was what this was for. It was cross-application serialization to a GPU, which didn't have any other implicit serialization. It's a pretty simple primitive. We also know these as events. If you go look at the Wikipedia article for events as a synchronization primitives, these have exactly the same semantics. In the Linux space, we know these as futexes. This is exactly the same synchronization primitives as a futex, which I happen to take advantage of course. It has a trigger, which means the fence goes from not triggered to triggered, and then it has an await. And you can come in and the awaiter will go up and slam up against the fence until it's triggered, and then all of the people waiting for the fence roar on through. And so it's a very low-level synchronization primitive, which is good for the implementer because it's really easy to implement it correctly, I think. It's bad for the application developer because it's a very primitive synchronization operation, and so the application developer is almost certain to get it wrong. But that's not my problem. I only have to use the semantic. This is awesome. Okay, and then of course you can reset the fence and you can query it without blocking. Pretty simple. In the world of 3D graphics and hardware, there are basically two models for how we manage queues of requests going to the graphics card. There's the single queue model, which is effectively what we do with Intel and Radeon and Nouveau stuff in the Linux kernel. There's a single API entrance point into the kernel, and requests are serialized through the kernel. Now, of course, in the actual hardware for Intel, there's like 4 request queues, but the kernel is exposing a logical single serialization by whoever gets back from the kernel first, their request is in the queue first. Other hardware implements multiple queues, and in fact, the NVIDIA hardware has is pretty much 1 queue per application. And the applications don't even have to negotiate with the kernel into when those requests are going to go into the queue. The hardware has its own scheduler. And so in the single queue model, serialization is really, really simple. All you have to do is know who got back from the kernel first, and you have a serialization guarantee. If you block until your friend gets back from the kernel, you know that your request to the kernel will be inserted after your friend's. Not a problem. Friend, enemy, whatever, other application. Sure, we all cooperate in the desktop because it's the happy, fun place to work. In the multiple queue model, you actually have to get the serialization all the way into the hardware. Okay, so The synchronous fence, the shared memory fencing that I'm doing doesn't do the multi-queue stuff because none of the hardware that I have exposes serialization guarantees in the hardware. All the hardware that I'm working on with free software has a single serialization point through the kernel. So I'm trying to build synchronization stuff on top of this single queue instead of the multi-queue stuff, which is harder. So I have a simpler problem. The sync fence that I need for DRI3000 is I need for the application to be able to tell when the X server is done with its buffer. The application is going to draw something into an image, hand it off to the X server is going to put it up on the screen. The application needs to be able to tell when it's done. Now we could do that with an X event. X events are pretty heavyweight and it involves a round trip. And I thought, well, you know, it'd be really cool if I could just have a little shared memory object that I could look at and see if the rendering was done. And it turns out to be really efficient this way. The other thing that you want to be able to do is you want the X server to be able to block waiting for your application to complete rendering to an object. And that's what you need in the MultiQueue model, right? You need the application to be able to say, here's the pixmap that I sent a bunch of requests down to I queued a bunch of stuff into the hardware for. You can't see my queue, you can't know when it's done, but you will be told by the hardware when that fence that I put in that queue, yeah, Ben?
Can you dose it by using a shader that never completes?
Oh yeah, absolutely. Yeah, welcome to the desktop. Ben was asking whether you can DOS the system by putting a shader into the system that never completes. And absolutely, you can DOS it. Now, of course, you can DOS the current single queue model because the single queue model doesn't ever stop. It executes everything to completion. We're trying to fix that. But currently, yeah, if you send an infinite loop shader to the Intel hardware right now, your infinite loop shader will execute for approximately infinite instructions until you power cycle. Yeah, if you keep going for 5 seconds, we'll actually kill the hardware and pull the power on the hardware and plug it back in, and then you keep going again.
What happens if you do that in WebGL?
So what happens if you kill the GPU in the middle of WebGL? Typically, you'll get the next frame rendered correctly because we'll reboot the GPU, and the next frame will get queued to the hardware and rendered correctly.
I was more thinking the other way around.
Oh, if the WebGL DOS is your hardware? Yes, then every 5 seconds your GPU will reset until you finally get around to killing Firefox. Yeah. Do you actually run WebGL applications?
I work with that. The Google Map does your Intel graphics just fine.
Just fine, absolutely. Yeah, don't do that. Yeah. Someday we'll get Intel hardware that actually lets you interrupt your execution of your requests. I hope. It would be awesome. Okay, so the shim fence history. Pthread primitives work across processes. Did anybody know that? You can stick a pthread mutex in shared memory, and you can actually have multiple processes. It's awesome. It's an optional part of the Pthread API, but Linux, of course, implements it because Linux does everything that's optional. It's supported by Linux. Oh, and also Solaris. Not so much BSD. Well, you know BSD. Did you know that it's horribly broken in Linux because you can't have it work between 32 and 64-bit processes? Awesome. All you have to go is look at the data type. It's like if def x86-64 additional structure member elements in the mutex. Oh, and by the way, it uses the int and long data types because why not? Yeah. Yeah, it's vastly different between the two architectures. So effectively, you cannot use pthreads between processes on Linux unless you know that they're all the same word size. Well, fortunately, the Linux Futex API can be used across processes. Yay! And you understand this is not a pthreads problem. This is a glibc problem, which cannot be fixed because the glibc API exposes the structure type from mutexes to applications, and so we're stuck with not being able to use pthread primitives. Oh well, I use Linux futexes. The awesome part about using Linux futexes is they provide exactly the semantics that I want. So the implementation for the X shared memory fence library on top of Linux futexes is about 1 line per function that says when you want to trigger a futex, you should trigger a X shared memory fence, you should trigger the futex. Yeah, it's pretty simple.
Do you mark futex as private if you don't need the process?
This is only interesting for shared memory processes. This is always used for shared memory stuff. So I'm not. This is explicitly for. Linus asked if I mark the futex for private to the process, and it's no, I don't, because I never do that. That's not what this is for. This is explicitly for synchronization between processes. I also went ahead and implemented the pthread version because it's actually useful on Solaris. And I like to make sure my software runs on portables on other systems, even if only crazy people run those other systems. Unlike other parts of the system these days. Yeah. Yeah. Sorry, there's another little project that I've been doing a little research on recently that's not portable outside of the Linux ecosystem. MIT shared memory. So the MIT shared memory extension, I created this in 1990 as an efficient way of getting, yeah, I know, probably before most of you were born. It was using the sysv shared memory interfaces, and the awesome part about the sysv shared memory interfaces, the shmget and shmat and shmcontrol, those lovely interfaces, they live in a global namespace which all applications can touch. The problem in the world of X is that the X application and the X server may be run by different UIDs. And if you're really lucky, the X server has no privileges in your system. But that means for the purposes of the MIT shared memory extension, the X server and the application have to agree about permissions to an object so that they can be accessed by any UID, like not you or the X server. And so it's kind of a disaster. So I re-implemented that API using file descriptor passing, where the application maps a file, where the file descriptor passes the file descriptor over a Linux domain socket to a local domain socket to the X server. The X server then pulls that file descriptor out and maps the thing. Bang, now we have a secure way of passing my shared memory between processes. Turns out to be really useful because sysv shared memory is a disaster. There's just 2 requests that I added to the MIT shared memory extension. Attach FD, which is to say I have a pile of shared memory attached to this file descriptor, and I'm passing it to you. And then a way for the application to say, oh, please, Mr. X server, why don't you just allocate a shared memory, a pile of shared memory for me and give me that file descriptor. The hardest part of the implementation of this, Rusty. Okay. The hardest part of the implementation of this was actually figuring out where tempfs was mounted. I have a long list of potential directories now where tempfs might be mounted by your distribution, and I hope I find it. Maybe I will. I don't know. Now Rusty has a question.
Can you use this to segfault the X server?
Absolutely! Yes, of course. That's my next slide. Thank you, Rusty. Okay, so now you have passed this file descriptor off to the X server, and you now share a file descriptor to the same piece of shared memory. What happens when the application uses our favorite syscall? This is one of everybody's favorite syscalls that always causes problems in the kernel. Yeah, it caused problems for me too. Somebody's going to call ftruncate on the file. So what happens when ftruncate is called? Well, all those pages, whoof, they're gone. And every access to that address space will now generate a SIG bus. Thank you. Thank you for the SIG bus. So what did I have to do now? Haha, now the X server traps the SIG bus, checks to see where the address was that generated the SIG bus. It has a little linked list to these shared memory blocks. This is, that one caused a SIG fault. Let me invalidate that one, and then I mmap some new memory in top of that so that I can return for my SIG fault handler and keep going. And I invalidate that XID so that the next time the user tries to use that shared memory block, they get errors back, which is kind of nice. And things go on. It's kind of nice. Yeah, at this point, I'm about 7 levels down in the nesting of, I would like to be able to fix DRI2, right? This is one of my, I found this image a couple of days ago. It's a rabbit shaving a yak, yeah. Yeah, I think everybody needs that. Okay, so after I got the the SIG bus handler, take care of all of that, then my MIT shared memory extension could demonstrate that file descriptor passing was working in Linux, and that I had a new fun utility, and I could move on to the next thing. Okay, so the next thing I needed to be able to support was a new GL extension called Extswap control tear. Okay, so why do we do page flipping in GL? Why do we do swapping in GL? It's so that we don't get those horrible horizontal lines that are tearing on our screen. We don't like those, right? Well, actually, it turns out that game users love them, or at least occasionally. The game developer would much rather have a few occasional tears on the screen than the other kind of visual artifact called judder, where you miss an entire frame. So the game application is running along rendering frames, and it's rendering frames. It takes 14 milliseconds for this one, 14 milliseconds for this one, 15 milliseconds for this one, and 16 and a half milliseconds for that one. Okay, so when the 16 and a half millisecond frame comes along and you're running at 60 hertz, you're going to just miss the V-blank window. Right? That 16 millisecond frame is just a little too long. And all of a sudden, if you insist that the screen only update at precisely at frame boundaries, that frame that took just a tiny bit too long is going to be displayed an entire frame beyond that. So it's going to get an additional frame of delay before it actually gets delayed. And for a user, what you're going to see is you're going to be panning smoothly across. You're going to get the 47 million polygon thing come on the screen, and all of a sudden it's going to go chunk, 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 and then it's going to keep going again. And that's really distracting. So the option, what this extension does is it says, hey, if I took just a little bit too long to render this frame, why don't you just tear? Stop displaying the old frame and start displaying my new frame, even if it means I don't get to see the whole frame. Typically what happens is a competent game, of which there are at least 3, we'll notice that it's gone just a little bit beyond its expected rendering time, and it will say, whoa, 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 that's terrible. We clearly have too many polygons on the screen. It'll crank down the complexity, and so the next frame will take a suitable amount of time to render. So the game will catch up. But the idea of this extension is that you get a tiny bit of tearing near the top of the screen instead of missing a whole frame. Okay, our hardware oddly supports this extension, but it was never exposed. And so I added all the necessary kernel API for Sandy Bridge and Ivy Bridge to expose this up through the DRM API. The way that I did it was as cheaply code-wise as possible. It's not really what I want. It does demonstrate that it works, but in particular under high GPU loads, it won't work very well. It may tear a lot later than you want it to, and that's kind of the case in question here, is when you're driving the GPU a little too hard. Right now, I actually stick the flip into this single request queue. And so if you have a whole bunch of rendering lined up in your request queue, the flip goes in here. And so all of that rendering that you are so busily waiting for because you put too much in the queue gets to execute before the flip. And so the tear happens a lot further down the screen than you want. The reason for that is it needs to be serialized with the rendering that went before. And so what I need to do is just pull it out of the queue, put an appropriate worker thread to actually do the appropriate blocking, and then hit the register directly. I don't think this will require a kernel API change, being that the API that we implemented was put into 3.12. It won't require an API change, but there may be a new API if the one that we specified before doesn't work. Isn't that how it goes? Yeah. Okay. XCB special events. XCB does not do callbacks. Why doesn't XCB do callbacks? Callbacks are an awesome way of having the application get involved in the deep processing in the middle of your library. Well, the problem with callbacks is if you're in the middle of processing, if you have some multi-threaded library and you're in the middle of processing some network activity and you want your library to call back into your application to say, hey, can you help me out with this network processing? Well, all of a sudden you have this locking disaster. You kind of, if you've taken 47 locks down to get to the bowels of your library, now you're going to call back out to your application. What do you do with all these locks? Well, what the XCB developers decided was they were just never going to deal with this case. It's easy to put your head in the sand, and there won't be any locking problems. The problem is that Mesa, our 3D library, has to be able to receive X events without the application cooperating at all. So the application can't be involved in seeing these events, in processing the events, because the application event loop is up in SDL, it's up in the application, it's processing mouse and keyboard events. It's not expecting to see these, oh, your buffer is ready for your use now, sir, events at all. And it's certainly not going to hand them back to Mesa. The way that we did this in Xlib is we put a callback in Xlib, because Xlib supports event callbacks. And Xlib would happily call back out to Mesa and say, hey, I saw this event, are you interested in it? And Mesa would just take the event and say, yes, thank you. And the event would never appear in the application's queue. Kind of a simple mechanism. Well, with XCB's position against callbacks, what are we going to do? Well, what I did was say, oh, wait a minute, I'm creating an all-new extension with all new events. Let me create them in a way such that XCB can easily tell which these magic events are and just take them out of the event queue and put them in a different event queue. So instead of putting them in the application event queue, I put them in a special event queue. I always expected to rename the special event queue to something a little less lamely named, but it's called the special event queue still. Think more about naming. So what it has is very hard-coded matching rules that match exactly the semantics I need for my new extensions, and that's it. And if you want to do different matching for different insertion into special event queues, you can add new API to XCB. It seemed like a good idea. Somebody actually proposed that I do some complicated masking and ORing and ANDing and comparing pattern matching language. And I said, you know, that would be an awesome plan. Let me think about that, and you can send me patches and I'll refuse them. Okay, so what did I need to do file descriptor passing? I need to do it in a bunch of different libraries. What I discovered is that libraries must absolutely be ready to receive file descriptors at any time. If you ever call read or receive without a spot to get the file descriptors, their file descriptors queued, they will just be closed and you will never see them. So your application cannot say, I'd like to do a read, and by the way, give me an error if there are file descriptors pending. No, 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 no. You have to have buffer space for your file descriptors. More than that, if you don't provide enough buffer space for all the file descriptors, the ones that you don't have space for will be closed because you didn't provide buffer space for them. Oh, thank you, POSIX APIs. Yeah, so right now I provide like space for 128 file descriptors, and the server is very careful never to give you more than that. If the client gives the X server more file descriptors than that in one write request, the X server is not going to get them. So your library better be careful. I had to hack up libxtrans. How many people have ever seen the glories of libxtrans? Yeah, this is a library in name only. It's actually, once we figured out what it was, when you do a make install in this library, it copies the C source files to your include directory, because that's how the library is used. Your target application includes the C files with magic flags to compile just the parts that you need. It's the best API ever. So I hacked up libxtrans for the X server and immediately, of course, broke the other user of the Xtrans library, the font server. And it's like, I don't think any Linux distribution packages the font server, but Solaris does. And so I got a bug report. Oh, you broke libxtrans for Solaris, the font server on Solaris. It's like, I'm so sorry. Fortunately, a patch was also provided, and I applied it, and it works now. Well, that's good. XCB for all the clients. One of the things I did not do was put file descriptor passing into xlib. If you really want to do file descriptor passing in xlib, you can keep both the pieces. That's really ugly. So I just did XCB. So anything using file descriptor passing needs to use XCB now. That meant adding file descriptors to the XML protocol description and the XML generators and the intrinsic pieces of XCB. XCB is a kind of a fun project. It's a code generating kind of project. Issues with DRI2. So what are we trying to solve here, right? Eric said, go fix DRI2. Well, here are the problems with DRI2. I have 2 slides. There are all the problems in DRI2. Buffer resize. When the application resizes its window, the X server would asynchronously resize all the drawing buffers and eventually tell the application. And the application would find out someday, oh, by the way, all the drawing you've been doing for the last 10 minutes, yeah, I threw that on the floor because I threw those buffers away. Hope you're okay with that. The DRI2 actually had all of the stenciling and depth buffers and everything else. The protocol supported having the X server allocate those. Why did it do that? Why is the X server allocating my rendering buffers? Well, it turns out that SGI in their infinite wisdom specified GLX this way, that if you had 2 GLX applications in different processes rendering to GLX to the same window, they must share all their buffers. Which was an awesome plan in 1989 when we didn't have threading. It turns out to be essentially impossible today. I don't know if it was accidental or intentional. Was it intentional that the depth buffers were broken, Eric?
I was aware.
Well, about 5 years ago, I gave a talk at Plumbers about how we deprecated interfaces in X. And here's another example of the policy and practice in practice here. The way that you deprecate APIs in X is you break them accidentally. You wait for years, usually 2 or 3 years, and you note that nobody has complained that you horribly broken these APIs. We broke an interface in Xlib to the point where if anybody ever called one of about 50 functions, your application would segfault. Right? Standard API in Xlib, we broke like 50 different functions. If you called any one of those, segfault instantly. 7 years later, we noticed, oh wait, that might be broken. Yeah, we deleted that code immediately. Obviously, nobody's using it. In this case, here's another case where we broke the code semi-intentionally for depth and stencil buffers. We hadn't broken it for the actual rendering buffers. But we noticed that no applications appeared to care, and so we said, fine, we're going to break it for rendering buffers too, because it's way easier. So DRI3 and the DRI3000 system is explicitly not conformant with GLX. And Ian Romanek and a couple of other GLX fanboys cried at us and said, but you're breaking compatibility. It's like, I'm sorry, we already did that a couple years ago. You could have whined then, too late. Yeah, that was a disaster. Other issues with DRI2, there was no support for integration with the composite extension. When a DRI2 application updated its buffer, you would get a blit into the Windows back buffer synchronized with vblank off screen. And then the composite manager would say, oh, look, somebody updated contents in this frame. Let me get that ready for next frame. So every time you ran a GL application in a window under DRI2 with a composite manager running, which is to say Gnome Shell or KWin or any modern desktop, you would have an absolute guaranteed additional frame of latency between your application's rendering and the presentation on the screen. Really awful. The other thing, of course, was you couldn't do DRI2 in XCB because of the event processing problems. The libDRI and Mesa right now actually use XCB for half of the DRI2 stuff and don't use it for the event part. I have a patch that just goes back to the old way that happens to fix a bunch of bugs in that. I don't know if I'll get the Mesa guys to take it or not. The other interesting thing was that DRI2 has this wonderful vblank synchronized update for the screen. Right? You can say swap buffers and your GL application gets synchronized to the screen. No other application in your system gets that functionality. So if you have a core GTK application that doesn't use GL, I'm sorry, you don't get vblank synchronization. If you have a compositing manager using the render extension like, say, Metacity, sorry, no vblank synchronization for you. And there's a whole bunch of GL extensions we just can't do. DRI3000 is split up into 2 extensions. In order to support the notion that you have this updating which is not tied to direct rendering. So the DRI3 extension does all the direct rendering stuff, and the next slide has actually the entire API for the DRI3 extension. It provides access to the DRM device so your application can draw using direct rendering. It shares DRM pixel buffers between the application and the server. These are RGB pixel buffers. That's all you can share, pixmaps. And then it's got this futex, the shared memory futex semaphore between the client and the server. And the present extensions where all the fun happens. It can copy or flip pixmaps to Windows. It's synchronized with vblank, and it's got a bunch of events.
They have to be RGB. They can't be YCBCR.
There is the present extension does not support YCBCR or YUV buffers. That's something that I'm hoping to add. I wanted to make sure I was presenting what we have today. Yes, I would love to do that. It doesn't seem hard. Here's the DRI3 extension. You could open something. You can create pixmaps in both directions, and you can move the fences back and forth. Here's the present extension. It's about equally complicated. You can take a pixmap and put it on the screen. That's pretty much the operation you get. Everything else is in support of that, and it's really all you get to do. You have a pixmap in the X server, and you put it on the screen. That seemed like a pretty simple operation. I call it present pixmap specifically because that's what it does. It does it with pixmaps. When we could add support for YUV or YCBCR or anything other crazy format by adding a new request that takes a new format of data. Really, really easy. That's what present pixmap looks like. Oh, the other thing is that all applications want the semantic. Right now, GTK applications, 2D GTK applications, or most other applications They always render stuff into an off-screen buffer and then blit it onto the screen because they want that nice seamless update. They want double buffering. But they really want vblank synchronized double buffering, and they can't have that today. The problem with using copy area is that the compositing manager has no idea when the application is done presenting a frame. If you use the present extension, and I have more magic in the future, the compositing manager is going to know, oh, that application is actually done with a frame. I can take that content and put it on the screen. That's an atomic operation. Yeah. And of course, OpenGL applications are always double buffered. So you want to double buffer all your applications. Present also offers some opportunities for optimization. If the application does multiple presents in the same frame time, the X server can just say, you know, the content that was going to be on the next frame, well, you're going to overwrite that with this new content. Let me just not do that blit. It's a pretty tremendous performance optimization for applications that are going faster than 60 FPS, like, say, benchmarks. It makes benchmarks look way better. Yeah. Benchmark optimizations. Well, it happens to be free. Why not? I have a hacked up Metacity that I'm using here that uses the present extension. So I have the simplest compositing manager I know of, the Metacity window manager, that is vblank synchronized. It's lovely. It was funny. I hadn't used a compositing manager for a couple of years. And I was scrolling around in, then I started using Metacity for a couple of days with present extension. I was happily scrolling around in Firefox showing stuff, you know, browsing some website. I turned off compositing and I started scrolling around again. All of a sudden, my eyes noticed the tearing. For some reason, my eyes had been filtering that out of my consciousness for years. And all of a sudden now, whenever I run a not vblank synchronized session on the screen, it's annoying to me now. I'm very sad. The main thing I'm doing this in Metacity for is it's very simple, and it's a basis for prototyping of presentation redirection, where the present request is passed to the X server and then handed to the compositing manager for it to do what it wants. And that's what I wanted to talk about last, future work. I didn't talk much about present redirection, which I'd hoped to be able to talk about because I wanted to make sure I only presented what I had actually done over the year instead of what I'd hoped to do over the year. I think it's only another couple weeks worth of work because I have all the architecture in place. And I'm hoping to be able to demonstrate that in a couple weeks. I was hoping to do the work over the Christmas holidays because that's always a great time for development. And actually, my cat intervened, of course. But also, it was really sad, but work intervened, and I had to support customers instead. As Ben said, we need to think about what to do about video. This is clearly a spot where YCBCR, YUV, or whatever other crazy video formats want to be put in. And then I want to think about per monitor pixmaps. Right now, when you do a presentation, the pixmap goes up on the screen, but inside the X server, there's only one screen pixmap for all the monitors. So the only way you get page flipping is if all the monitors are showing the same image. But the hardware is happy to have only one monitor page flip at a time. I think it's going to be a totally transparent hack to the clients to be able to page flip on a per monitor basis. And that means in a multi-screen environment like this, you'll be able to run a 3D application up here and page flip that without touching the monitor down here, which will be pretty cool. I think that's what we have time for. Thanks so much for coming out to see the last presentation of today, and I hope we have a great day tomorrow as well. It's supposed to be wicked hot. Make sure you drink lots of water and wear your sunscreen. Yes, of course we have time for questions. Questions or comments today? No, you may not. What? It's okay, Early D. I slept through your talk too. But yeah, you actually you're the. One of the other things that I didn't talk about was the fact that DRI2 and had been hacked to support Early D's multi-GPU stuff called Prime, and where you could have like a USB attached display. And have that use the internal renderer for rasterization, or you could have an internal renderer that didn't display anything at all. The Present API, Present protocol has support for telling me which what are they called? Provider. Which provider you want to be working with, and that's in the protocol, and it's dropped on the floor because I don't have any hardware to test it on. And so I think the protocol is fine with this because because you actually get a provider in every present request. So I think it'll work. I just need to hack up the code to actually try it. So it'd be lovely if you could like demonstrate how it should work. I think it's like 2 lines of code. Take the provider ID, look up the appropriate object, and pass it to that thing instead of the current screen. Question?
You didn't mention Wayland at any point. Obviously continuing the pace, still improving the X server.
Yep.
Because you don't see Wayland ahead, or?
I know that I will continue to be using X for a long time because most of my applications are X applications. I don't see any particular value in using another level of indirection under my Windows system today. Given the applications I want to run are X applications, I don't see the marginal desktop that I run XFCE moving to Wayland anytime soon. So, and in any case, this work is relevant for X applications. So if you're running X applications in any environment, this work will improve the performance of them. So if you wanted to run X on top of Wayland, this will help there as well. You get the main thing is here, present is giving you that atomic frame for every application instead of just GL applications, which is precisely what any Windows system wants today. It wants to be giving an atomic notification of this application has provided a new frame. Please put it up on the screen. So if you're running X on top of Wayland, that present pixmap request is precisely when you want to send that off to Wayland. So it happens to work better with Wayland, but it also happens to work better with real hardware or with any other compositor. Let's go back out in the sun, guys. Thanks so much for coming today.